Hi, everybody. All right, well, let's continue. So now I'd like to go on and talk about quantum wires. Quantum wires are one-dimensional nanostructures. So they're confined in two directions and extended in one direction, all right? And I'd like to talk about how these are made. We'll talk about two types, semiconductor nanowires and carbon nanotubes. And then we'll talk very briefly about energy levels before we go on to our next system, okay? All right, so we're continuing our discussion of nanostructures to talk about nanowires, one-dimensional systems, all right? Confined in two directions and extended in one direction. Here are some examples of semiconductor nanowires. You can see what they look like. Well, they look like they have nanometer dimensions in two directions, but they're extended in the third direction, okay? These are silicon nanowires grown at UC Berkeley. Here's some indium gallium arsenide nanowires grown at Lund University in Sweden, where I had a chance to visit a few years ago. This is actually a scanning tunneling microscope being brought up to the end of one of these tips, but that's beside the point. Let's go ahead. So how are these made? So semiconductor nanowires can be made this way. They can be made with molecular beam epitaxy, interestingly enough. What's done is the following. First, in this particular process, gold nanoparticles are deposited on the surface. And then silicon atoms are deposited after that. And what happens is that the silicon preferentially wants to grow underneath the gold nanoparticles. The gold catalyzes the adhesion of the silicon atoms to the existing surface. And so the material grows faster underneath the nanoparticles. And that leads to the formation of nanowires or nanopillars. Okay? Here's an image of these. In the first case, I think the gold nanoparticles were deposited. And then you can see the nanowires growing up. This shows the tip of one of the nanowires, and then an electron microscope image of just this portion of the nanowire, showing that you really do have crystalline growth. And then on top, you can see the gold nanoparticle. So those are semiconductor nanowires. The other type, arguably the most famous type now, are carbon nanotubes. Carbon nanotubes are, well, as you can see, they have this shape. They're like a sheet of graphene that's been rolled up into a tube. And these tubes can form, and they have dimensions that can vary. Their diameter can vary between 0.4 and about 2 nanometers, so very small. But their length can be very extended, up to 5 or 10 microns. So many thousands of times longer than they are wide, okay? Interestingly, you can have both single walled carbon nanotubes and multi-walled carbon nanotubes. In this case, you have nested tubes, one inside of the other. That's sort of interesting too. When they're grown in when they're grown, you often get a combination of these two types, and then there's one needs to separate them. Here's some electron microscope images. First, of single-wall carbon nanotubes. You can see the dimensions of the nanotube here, and you can see this is an atomic resolution image, so you can see more or less where the atoms are in the surface system. You can see the crystalline order. And then this is a multi-wall carbon nanotube, and you can see that it consists of many different layers, sort of like an onion, if you like. If an onion were stretched out into a tube and then made really, really small, well, that's what it would be. Here, let's talk briefly about how carbon nanotubes are made. So carbon nanotubes, like the other carbon nanostructures, they actually occur anytime that carbon is well, for example, they occur in things like candle soot, that black soot that you get when you have a smoky flame. That's full of all sorts of carbon nanostructures, like carbon nanotubes and fullerenes, and all kinds of things. But to make these in a deterministic way so that you get what you want, they can be made by chemical vapor epitaxy, where methane or another hydrocarbon gas is decomposed over a catalyst in a furnace. And the way that this typically works is like this. The hydrocarbon gas decomposes over a catalyst. The catalyst consists of small particles, and the carbon is deposited around the particles. And then because of the shape, instead of forming like a graphene sheet, instead it organizes itself into a tube. And as it continues to grow, it pushes this tube out. And so then the reaction continues to occur at the catalyst, and it pushes a carbon nanotube out from it, grows out from it. Okay? So here's a simulation of what should happen. And then these are electron microscope pictures, which appear to show the growth of a carbon nanotube. Here are some carbon nanotubes that have been grown, just so you can see what they look like. Here they are growing vertically from a substrate in a very dense pattern. Looks really neat. Okay, so the catalyst particles are all down here. And here that's what they look like after they've been removed from the substrate. And this shows you one of the issues with these materials. Here it looks like a kind of a ball of yarn. So it's possible to grow these things. It turns out under some conditions you form carbon nanotubes that are conducting. In some cases, in other conditions, they're semiconductors. But in general, they're all mixed up and tangled together in a big random array, which makes it hard to use them for any purpose. Okay, it's like a bowl of spaghetti, I guess. Okay, here, let's pause for a second. All right, here, I want to talk briefly about energy levels in nanowires before we go on. All right, so we're talking about energy levels in quantum wires. And what I want to say is just this. In these systems, of course, the electron is confined in 2 dimensions. Okay, that means that the electron wave function will be confined both in the vertical direction in this map and the horizontal direction. Okay, but in the 3rd direction, it will be extended. So because of this, we get just as before. We can calculate confinement energies associated with each of these types of confinement, and we'll get a series of energy states. I'm not going to bother and go and calculate them right now. But then in addition, the electrons are free to move along the direction of the wire. So they can have kinetic energy in the 3rd direction. So once again, we get subbands, much like we saw for quantum wells. Okay? So if the direction along which the particle is free is the x direction, then kx can vary. And so we have different confined subbands with a variable amount of kinetic energy in the x direction. All right, well, I'm not going to go into any more detail about quantum wires. Instead, I'd like to go ahead and talk about quantum dots. Okay, so let's talk about the 3rd class of nanostructures. These are quantum dots or nanoparticles. So particles so small that the electrons show confinement effects due to confinement in all 3 dimensions now. Okay? And once again, we're going to talk about how these are made, and then I'd like to talk about energy levels in these systems. Okay? All right, let's go ahead, shall we? So now we're talking about quantum dots, these little particles where electrons are fully confined. So first, nanoparticles like this can be made in a number of different ways. So I'm just going to concentrate on the 2 that are the most important right now. And they're also the 2 ways that produce very highly ordered crystalline particles that all, where you can make a whole collection of them. They're all have the same properties. The first are what are called self-assembled quantum dots, and they can be made by molecular beam epitaxy. In this case, we grow on top of a semiconductor. We start to deposit another semiconductor, but in this case, that we make it so that the lattice constants of the 2 semiconductors don't match. And under certain conditions, the new semiconductor, perhaps this is indium arsenide being deposited on indium phosphide, the new semiconductor will want to grow islands instead of growing continuous layers. So the indium arsenide atoms will agglomerate into islands like this. Then this will happen, and the size of these islands will be determined by how much indium arsenide you've deposited. And at some point, when you have the dots that you want, you can then switch back to growing indium phosphide and cap the dots. Now you have these indium arsenide small bandgap semiconductor quantum dots inside of a matrix made of a larger bandgap semiconductor indium phosphide. Here's what one of these dots looks like in an electron microscope image. So you can see the island here, surrounded by the other semiconductor. Okay? So that's one way of growing these. And what's nice about these quantum dots is that they're already embedded in a semiconductor. So if you wanted to build an electronic device around them, you're sort of all ready to go. Okay? The other way to make these is through chemistry, to make what are called colloidal quantum dots. In this case, through a chemical process, you get nanocrystals of a semiconductor to grow. They grow at a certain rate, and by carefully controlling the reaction and controlling how long the reaction proceeds, you can control the size of the quantum dots. This can be done with very simple equipment. I think they made some upstairs in the chemistry department a few years ago, and you can buy them commercially, and they're also made in large quantities for different applications, as we'll talk about. But this is kind of how it works. You have this chemical reaction, which you quench very rapidly to get nanoparticles of a certain size. Typically, the material used for these is a semiconductor called cadmium selenide, although there are other semiconductors that have been used as well. Okay. And that's how quantum dots are made. All right. Well, the next thing I'd like to talk about are energy levels in quantum dots. And here we'll see things look quite different than the other 2 systems. Because the electrons now are going to be fully confined, we'll get discrete energy states in a quantum dot, just as we do in atoms. So sometimes quantum dots are called artificial atoms. But here, let's stop this video, and we'll talk about the energy levels in the next one.